Hello learners, I am Dr. Subhalakshmi Lamba. I belong to the School of Sciences of Indira Gandhi National Open University. And today we are going to talk about the kinematics of angular motion. For those of you who have enrolled in the BSc General program under CBCS at IGNOU with a physics elective as one of the subjects of choice, then you know that the course of physics that is offered in the first semester is mechanics. The course code of mechanics course is BPHCT 131. Before I go into the details of today's topic, let me just give you a brief recap of what the course of mechanics is about. The course of mechanics consists of 4 blocks. The first block is the block on mathematical preliminaries, in which you study the basics of vector algebra and the basics of ordinary differential equations. You will study first order ordinary differential equations and second order ordinary differential equations. This will help you to cover the remaining blocks. The remaining blocks, the focus is on mechanics. So in block 2, you study the basic concepts of mechanics. In block 3, you study rotational motion and many particle systems. In block 4, you study harmonic oscillations. All this is covered in 19 units. And today, we are going to study the first unit of block 3, which talks about the kinematics of angular motion. The motion of objects is a familiar topic to you. Motion is all around us. You may have seen that objects move in different ways. Mechanics is the study of motion, and we divide the motion of objects into 3 fundamental types of motion. The first type of motion we study is translational motion. When we study the translational motion of objects, you realize that there is actually a change in the position of the object. The second type of fundamental motion that we talk about is rotational motion. In the rotational motion of objects, you have objects that are spinning or turning about a fixed axis. The third type of motion is oscillatory motion, and in this, the object is going to and fro about a point. Sometimes you encounter motion which is a combination of 2 of these types of motion. You may have a combination of translation and rotation, or you may have some other more complicated type of motion, but that falls under the category of general motion. Now, how do you study motion? Mechanics, as I told you, is the study of motion. You study motion in basically 2 aspects of motion. You study the kinematics of motion and you study the dynamics of motion. How do you study the kinematics of motion? In the kinematics of motion, you study motion, the various aspects of the motion of objects or particles or even systems of objects without any reference or without going into the details of what is causing that motion. So basically, you just put up the kinematic equations of motion, and these equations are used to derive the variables, the kinematic variables which describe the motion, which are basically the position, the velocity and the acceleration. What do you study when you study the dynamics of motion? In studying the dynamics of motion, you actually delve into the reason why the motion is taking place. So basically, in block 2, you have studied both the kinematics and dynamics of motion with a special emphasis on one particular type of motion, which is translational motion. So in block 2, you have studied Newton's laws of motion, the concepts of force and mass. You have applied Newton's laws of motion to different types of forces, for example, tension, friction, gravity. You've also studied the dynamics of circular motion. However, as I said, the focus has always been on translational motion. So, what is it about translational motion that is so important? Now, in this type of motion, you will realize that all points of a moving body have velocities and accelerations that are the same in magnitude and direction at every instant of time. This particular property of translational motion makes it easy for us to describe translational motion in the Cartesian coordinate system. So what are the different types of translational motion that you have studied? You have studied motion along a straight path. So this is not very common in nature, but you have some examples. For example, a car moving on a road, a train moving on a railway track. Remember, when I talk about the train moving on a railway track, I'm not talking about the movement of the wheels. I'm talking about the general motion of the train as a whole on the track. So that is an example of motion along a straight line. Similarly, the up and down motion of the lift, the motion of a freely falling ball, which is thrown, say, maybe from a balcony. There are other types of straight line motion, like the motion of a bullet fired from a gun, or when you have a box sliding down an inclined plane. These are all examples of straight line motion. If you remember your studies of block 2, you know that we have described this kind of straight line motion using the Cartesian coordinate system, and you generally describe this motion using just the x coordinate. However, as I said before, straight line motion is not that common in nature. More often, you have motion that takes place along a curved path. A very common example of this is when you kick a football into the air, or when you have a cricket ball which is being hit by a bat and it is set out into space, and you want to follow the path of that ball. So you study what is known as projectile motion. If you understand, projectile motion is a motion of an object which has been launched into space, but the motion takes place in a plane. So now you analyze this motion by treating it as a combination of two one-dimensional motions. That is, you study this kind of a motion in a two-dimensional Cartesian coordinate system. You solve the equations of motion that you are familiar with from one-dimensional motion. You solve these equations of motion along the x direction and the y direction, and finally you connect the x and y variables to get an expression for the path of a projectile. You are familiar with this, and you have done it even in your +2 physics as well as in block 2 of this course. So this is an example of motion in a plane, which is a motion in 2 dimension. It is translational motion, and it still has the property that the velocity and acceleration at every point of the moving body is the same with time. Another kind of familiar motion, translational motion in 2 dimensions, is circular motion. So you have an example of a car moving on a circular racetrack. This is motion in a plane. Again, you could describe it using the 2-dimension Cartesian coordinate system. Today we are going to talk about the kinematics of angular motion. Now, why do we want to talk about angular motion specifically as opposed to translational motion, which you have studied in the previous block, that is block 2 of this course? So for that, let us first understand what do we mean by angular motion. So angular motion is motion either about a fixed point or motion about a fixed axis. When we talk about motion about a fixed point, what is an example of this? You can think of tying a stone at the end of a string and swing that string in a circle. You could swing the string in a vertical plane or in the horizontal plane, and that is an example of motion about a fixed point. Very common example of motion about a fixed point would also be the motion of the planets about the sun or motion about the satellites around the earth. So these are all examples of motion about a fixed point. When we talk about motion about a fixed axis, what are we talking about? This is very commonly seen around us. The motion of any type of wheel is actually motion about a fixed axis. You have the hands of a clock, you have the motion of a merry-go-round. All of these objects are rotating about a fixed axis, and that is true even of a spinning top. So either you're talking about motion about a fixed point or motion about a fixed axis, and these are what comprises angular motion. So as I said before, how did we study translational motion, which you have studied in block 2? You made a choice of kinematic variables. What are your kinematic variables? These are position, velocity, and acceleration. When you study translational motion, you use the Cartesian coordinate system. In one dimension or for translation motion along a straight path, you use the x coordinate. When you were talking about projectile motion, which is translational motion in 2 dimensions, you used the x and y coordinates, but still we were sticking to the Cartesian coordinate system. Now, what is special about the translational motion is that when you do 2-dimensional translational motion, you can split it into 2 one-dimensional translational motions and then connect the 2 to get the effective motion of the object. Now, when we talk about angular motion, we do not use the Cartesian coordinate system. We set up a different set of kinematic variables which are analogous to the variables you use for translational motion, but they are not the same. And the reason we do that will become clear as you study the rest of this unit. However, at this point, I will just say that when we describe angular motion, it becomes convenient to use a set of variables, a set of kinematic variables that are different from those you have used when you are studying translational motion. And these are the set of kinematic variables that we are going to use to study the motion of planets around the sun and the rotation of a body about a fixed axis. As always in physics, when we start studying a new topic, we start with the simplest system possible. When you started studying translational motion, you talked about motion along a straight line. So when you study motion along a straight line, you just need one coordinate to describe that motion. When we start our study of angular motion, we are going to once again start with the simplest possible example of angular motion, which is circular motion. In fact, for most of this unit, we will be concentrating mainly on circular motion, which could be uniform or non-uniform, and I would explain that later when we study the rest of this topic. So let us now say what are we going to study when we study the kinematics of angular motion. To start with, as I said, we will describe the kinematic angular variables, which are angular position, angular displacement, angular velocity, and angular acceleration. Now, you may have noticed that this is the same, or these variables are analogous to what you have set up for translational motion. In translational motion also, you have studied the position, the displacement, the velocity, and the acceleration. However, these are angular kinematic variables, and I shall be describing them. Next, you will set up the kinematic equations for angular variables. These very angular variables that you define here, you're going to set up equations for them so that you can find the basic properties of angular motion by using these kinematic equations. You will be determining the position, displacement, velocity, acceleration, all as a function of time using the kinematic equations. At the end, we have to relate the variables for angular motion and translational motion. It is not necessary to describe angular motion using angular variables. As I said before, we do it just for convenience. However, you can relate the angular and variables to the corresponding translational variables for the same motion, and that will make it clear why we prefer to use angular variables to describe angular motion. So now, as I said, we are going to start with the study of circular motion. So you can see that let us consider a particle moving in a circular path and the motion is counterclockwise. Just to explain, when we say counterclockwise, we mean that the sense of movement in the circle is opposite to the sense in which the hands of a clock move. So basically, you're going opposite to the direction in which the hands of the clock move. So this is counterclockwise motion. The particle is P. It is moving in a circular path and the center of the circle is O, and this is the a point through which the axis of rotation passes. So basically you have a particle P moving in a circular path about a fixed axis of rotation. If you consider that the circular motion is motion in a plane, so definitely it can be described by a two-dimensional Cartesian coordinate system. So if you consider that the particle is moving in the XY plane, then the axis of rotation, as you can see here, is along the positive Z direction. Once again, I emphasize, I'm talking about counterclockwise motion, and the axis of rotation passes through the center of the circle. Why is circular motion so important? Let us understand that also. Now, suppose you take a spinning wheel. This could be the wheel of a bicycle or any such rotating wheel, and you see that I have picked a point P on this wheel. Say it's a point on one of the spokes of the wheel. Now, if you analyze the path of the point P on this rotating wheel, the axis of rotation passes through the center of the wheel and it is at right angles to the plane in which you have the wheel. You will see that the point P will trace out a circular path. This is again rotating counterclockwise. So what I want to tell you and emphasize also is that if you take a point on any rotating body, then you will find that that point will always trace a circular path, and the center of the circular path will be the point through which the axis of rotation passes. So basically, when we talk about a particle moving in a circle either clockwise or counterclockwise, that particle could also be a point on any rotating body which is rotating about a fixed axis. So now let us describe the angular variables for this point P which is moving in a circular path, and the center of the circle is the point through which the axis of rotation passes, and the axis of rotation is perpendicular to the plane in which the circular motion is taking place. So we start with defining the first kinematic variable for angular motion, which is the angular position. Now here you see that I have drawn the xy coordinate system and I have put the circular path that is being traced out by a particle. Let us assume that the particle starts its motion from the point A, which is located on the x-axis. The center of the Cartesian coordinate system is the center of the circle, and OA is the radius of the circular path. Okay, and I say that at the time t is equal to 0, my particle is at the point A, and OX is the reference axis. Now suppose a time t elapses in which the particle moving counterclockwise reaches a point P on this very circle. So what do we know about the point P? We know that as the particle moves from A to P, it has traced out an arc length of S. That is the length traveled by the particle along the circle. So it is the arc of the circle defined by AP. Now want to know, how do we locate the point P in the plane? You can define the position in terms of the Cartesian coordinates, that is the x and y coordinate of the point P. You also have a radial vector which starts from O and ends at P and defines the position in terms of the vector r. You can also define an angular position for the point P. What is this angular position? It is the angle traced out by the radial vector as the particle moves from the point A to the point P. So basically you can see that the radial vector has swept out an angle theta. What is the measure of theta? Now you are familiar with denoting angles in terms of the degrees. However, here we introduce a new measure for the angle, and that is called the radian. What is the radian? The radian is the length of the arc, that is S, divided by the radius of the circle. What is the radius of the circle? That is given by OA. So basically it is the magnitude of the position vector at any point on the circle. So if you want to define the angular position in terms of radians, you have to say that theta, the angular position, is equal to S by R. Now S is a unit of length, has a unit of length, and S has a unit of length, and the radius obviously also has a unit of length. So when you divide S by R, what you get is an angle in radians. So this is the definition of radian. Angular position theta is equal to S by R. S is the arc length, R is the radius. Both have units of length. And when you divide S by R, you get theta in radians. Now, suppose you start the motion of the particle from the point A, and let us say that the particle completes one complete revolution of the circle and comes back to the point A. So it has essentially completed a full circle. So what do you say is the angular position? Is it 0? No, because angular position is the angle that is traced out by the radial vector which defines the position of the particle. So basically the radial vector has swept out an angle of what you are familiar with, 360 degrees or a complete circle. So now what is the angular position? You know that the angular position is defined as a ratio of the arc length covered along the circle divided by the radius of the circle. Now in one complete revolution, the distance covered by the particle along the circumference of the circle is nothing but 2 pi r. R is the radius. So the arc length is 2 pi r. If you divide that by the radius, you get that in completing one revolution, the angular position has changed by 2 pi. So the angular position for one complete revolution is 2 pi radians. Also, if you want, you can connect radians to degrees. How? Because you know that one full revolution is equal to 2 pi radians. You also know that one full revolution is equal to 360 degrees. Using this connection between radians and degrees, you can convert from a radian to a degree and vice versa. So 1 radian is equal to 360 by 2 pi degrees, and from this you can convert from degrees to radians as well. Now, as I have explained, one complete revolution is 2 pi radians. What if the particle makes 2 complete revolutions? Then the angular position is 4 pi, which is 2 pi into 2. So basically, if you do n complete revolutions, the angular position will be 2 pi n. After completing n revolutions, if the angular position comes to a stop at a position given by phi, which is the angular position with respect to the reference axis, then the actual angular position will be 2 pi n plus phi, as you can see in this particular slide. Now, when you study translational motion, let us think of translational motion along a straight line. You know that you are using the x coordinate to describe the motion. You say that when the particle moves to the right, that is, it moves along the positive x direction, you give it a position with plus x. When it moves to the left, it is moving along the negative x direction, you say that its position is given by minus x. What happens when we talk about circular motion? Now, as I have said, so far we were talking about counterclockwise motion, that is, it was moving from x towards the y direction along the circle. This is the direction in which the particle was moving. But you can also have clockwise motion in which the particle would move in the opposite direction. Say it would move from y towards x along the circle. Now, is there any way in which you can say by looking at the angular position whether it is moving clockwise or counterclockwise? So far, we have not said anything about that. So basically, just to distinguish between counterclockwise and clockwise motion, we develop a convention in which we say that if the particle is moving in the circle counterclockwise, the value of theta will be positive. If it is moving clockwise, it will be negative. So in this way, by just looking at the sign of theta, you will know whether your particle is moving clockwise or counterclockwise along the circular path. So let us do a quick example in which we connect the arc length and the radius to get a angular position in radians. Now, so all of you are familiar with CDs. Let us assume that you have a rotating CD. The CD is rotating counterclockwise, and we say that at any particular instant of time, a point P on the CD is located at an angle theta, and at that point it has an arc length, it has covered an arc length of 6 centimeters and the radius of the CD is 6.05 centimeters. So, can you give a value to theta? How do you do that? We know that the angular position theta is nothing but S, which is the arc length, divided by R. Now, I have told you that the arc length is 6 centimeters, the radius of the CD is 6.05 centimeters, and if you divide the two, so you divide 6 by 6.05, and you will get that the angular position in theta is nothing but 0.992 radians. So basically in this question we have converted the arc length, which is a distance covered by the point P along the circular path, to an angular position theta, which is measured in radians. For this you have to know the radius of the circular path. Now this we have talked about counterclockwise motion. What happens if you were moving clockwise? If you were moving clockwise, then instead of moving from x to y along the circular path, you would be moving from x to minus y. So basically, instead of locating the point at P after a time t, you would be at a point P1. And in this case, your theta would be negative because you know that the angular position for clockwise motion is always negative. Learners, let us now summarize what you have studied in this lecture. Basically, we first introduce what is angular motion. That is because we want you to understand what are the systems of motion to which you can apply the techniques that you learn in this video. Next, we talk about the kinematic variables for angular motion. These are angular position, angular displacement, angular velocity, and angular acceleration. You would have noticed that these variables are totally analogous to what you learned for translational motion. Next, we define angular position. So basically, the angular position of a particle in circular motion about a fixed axis at any instant of time t is given by the angle theta that its position vector makes with respect to a fixed reference axis which passes through the center of the circle in which the particle is moving. We introduced a new measure for angle, which is called the radian. The radian is the ratio of the arc length to the radius of the circle in which the particle is moving. So basically, theta is S by R and S by R is in radians. You would also remember that we said that for one complete revolution of the particle, that is, when the particle starts from the point A and comes back to the point A, it covers an angular distance of 2 pi radians. Finally, we decided that we have to allot a convention which tells us whether the particle is moving in the circle in a clockwise or a counterclockwise direction. These are the only two ways in which a particle can move in a circle. So basically, we decided that theta is going to be positive for counterclockwise motion and theta will be negative for clockwise motion. In the next lecture, we will define the remaining angular variables, the angular kinematic variables, and also introduce the kinematic equations for angular motion. Thank you for watching this video. I hope to see you soon in the next lecture.